So now in chapter 5.2, we're going to be continuing and getting into more trigonometry. It's right triangle trigonometry. So something that I'll probably mention a lot is when you think about trigonometry, there's three main ways that you should think about it. You should think about right triangle trigonometry. You should think about the graphs, which we'll be getting into. And you should also think about it in terms of the unit circle, which we'll be getting into. So starting off with right triangle trig. So a right triangle is just going to be a triangle that contains a 90-degree or a right angle in it. And it's important to keep in mind that the hypotenuse is always going to be the side that is opposite the right angle. So here's a triangle, here's a right triangle. We can see it's a right triangle because we have this little square angle, which means 90-degree angle. The hypotenuse is the side opposite it. And we also have two other sides then, which we call one of them adjacent, the other one hypotenuse. The adjacent side is going to be the one that is directly forming the angle, and the opposite side is going to be the side that the angle is opening up towards. Okay, so for the trig for right triangles, we have our 6 trig functions. We have sine, so I wrote them down here with their abbreviations. We have sine, cosine, tangent, cosecant, secant, and cotangent. So what these trig functions are, in a sense, are just ratios of all the possible ratios of the sides of a right triangle. So sine of theta, let's look at sine first. So this is like a predefined function, kind of like when we were dealing with logarithms. We had to take the log of something. We needed an input. It's the same concept here. It's the sine of something. It's the sine of theta. That's the input value. So the sine of theta, which is our angle, it equals the opposite side divided by the hypotenuse. It's just a ratio for the lengths of the sides. Cosine of theta equals adjacent over hypotenuse. Tangent of theta equals opposite over adjacent. And cosecant equals hypotenuse over opposite. Secant equals hypotenuse over adjacent. Cotangent equals adjacent over opposite. So these are just all of the possible combinations for ratios of the side of a triangle. And you may notice I put them in this certain order on purpose. The main 3 are sine, cosine, and tangent. The other ones are just the reciprocal of the one above it. So sine and cosecant are reciprocals, cosine and secant are reciprocals, and tangent and cotangent are reciprocals. So a way that you can remember this, thinking about these first 3, sine, cosine, and tangent, which you probably remember, you can think of it as SOHCAHTOA. So that means for the SOH, sine is opposite over hypotenuse, so OH. Cosine is adjacent over hypotenuse, so AH. And tangent is opposite over adjacent, so OA. So that's SOHCAHTOA for the main 3 trig functions. Okay, so for the next thing that we have to know is the Pythagorean Theorem, which I'm sure that we all kind of remember. The Pythagorean Theorem relates the sides of a triangle together. So the Pythagorean Theorem tells us that a squared plus b squared equals c squared, where c is the hypotenuse. So notice that c is on the right side by itself. It doesn't matter which one you call a, which one you call b, but it does matter which one you call c. It has to be the hypotenuse. So let's do some quick examples with that before we get into a little bit harder questions. So let's find the missing side for each right triangle. So the first one we're missing the c. So we have a and b. C is the hypotenuse, which is missing. So we know that we're using the Pythagorean theorem. So it is important to note that this is only true for a right triangle. There is something else called the law of cosines when it's not a right triangle, and the law of sines, but for now, Pythagorean theorem, it only works with the right triangle. So filling in our values here, we have 3 squared plus 4 squared equals c squared. That's going to be 9 plus 16 equals c squared. 25 equals c squared. Take the square root. We get c equals 5. So remember that technically what we would get here is plus or minus 5 when we take the square root like that of both sides of an equation. But since we're dealing with lengths, it's only going to be positive 5 that we're using. So notice that these are all whole numbers, right? We have the sides of a right triangle are 3, 4, and 5. They're whole numbers. When we have the sides of a right triangle that are whole numbers that satisfy the Pythagorean theorem, that's something called Pythagorean triples. Okay, next one, we have these 3 sides and we're missing b. So we're going to use Pythagorean theorem, a squared plus b squared equals c squared. We plug in our values. 1 squared plus b squared equals 3 squared. That's 1 plus b squared equals 9. We subtract 1 on both sides. We get b squared equals 8. When we take the square root of both sides, we get the square root of 8. We should get in the habit of simplifying this. The square root of 8, we can rewrite that. I'll do it over here on the side. We can rewrite the square root of 8 as the square root of 2 times, I'll put 4 times 2, which would equal the square root of 4 times the square root of 2, which equals 2 radical 2. So that's the radical in simplest form. So I chopped it up like that because one of the factors, 4, was a perfect square, so we can simplify it using that method. Okay, so let's do an example with that same idea, but a little bit harder here. So find the value of each of the 6 trig functions of theta. So we want sine of theta, cosine of theta, and all of the rest of them. So we have our theta right here. So we do not have C. We have side A and side B. We do not have side C, so we need to actually find that. So I'm going to find that down here. A squared plus B squared equals C squared. So that's going to be 5 squared plus 12 squared equals C squared. So if we solve that for C, we'll end up getting C equals 13. We get 169 equals c squared, square root both sides, c equals 13. So that's going to be our side over here. Okay, now when we want to find the trig functions, we have sine of theta. Let's do sine of theta first. So sine of theta is opposite over hypotenuse. The opposite side is 5, so once again the angle's right here. The opposite side is 5 and the hypotenuse is 13. So this is going to equal 5 over 13. Next, for cosine, cosine is adjacent over hypotenuse. The adjacent side is 12, so that's 12 over 13. For tangent, tangent of theta is opposite over adjacent. That's 5 over 12. And now for the next ones, we'll do cosecant. Once again, I'm doing it in this order and writing it this way for a reason because of the reciprocal identities, which I'll formally mention in a few pages. So cosecant is hypotenuse over opposite, which is 13 over 5. And we have secant next. Secant theta is going to be hypotenuse over adjacent, which is 13 over 12. And lastly, cotangent of theta is adjacent over opposite, which is 12 over 5. Okay, so those are our 6 trig functions in terms of theta. Let's do one more here. So let's find the value of each of the 6 trig functions. So we have our hypotenuse. We have one of the other sides. We don't have A. And also keep in mind that theta is up here this time. Okay, so we need to find A. So we'll find it down here. A squared plus B squared equals C squared. We plug in our values. A squared plus 6 squared equals 8 squared. That's a squared plus 36 equals 64. We subtract 36 on both sides. We get a squared equals 28. 8, take the square root, and we get a equals the square root of 28, or we can simplify that to square root of 28 would be the square root of 4 times 7. Square root of 4 is 2, so 2 radical 7. Oops. So that's going to be our a value. I'm going to use 2 radical 7. Okay, so now finding the trig functions, we're going to look for sine of theta. Sine of theta is opposite over hypotenuse. So the opposite here is 6 because theta is on the top. So it's going to be 6 over 8, which we can simplify to 3/4. Cosine of theta is going to be adjacent over hypotenuse, which is going to be 2 radical 7 over 8, which simplifies to radical 7 over 4. Tangent of theta is going to equal opposite over adjacent, which is going to be 6 over 2 radical 7, which is going to be 3 over radical 7 after we simplify it. So we have to remember how to rationalize denominators. Radical 7 is not a rational number, meaning its decimal representation would go on forever and never repeat itself. So to rationalize denominators, we would multiply the numerator and denominator by radical 7. That would give us 3 radical 7 over 7. For the denominator, radical 7 times itself. The radicals cancel, we're just left with 7. So it's a little bit messier, but hopefully that's okay. So next for cosecant. Cosecant would be 8 over 6, which would give us 4 over 3. For secant of theta, that would give us 4 over radical 7. So it would give us 8 over 2 radical 7, which simplifies to 4 over radical 7. We could rationalize that denominator. It would give us 4 radical 7 over 7. So once again, if you need to remember how to rationalize a denominator, definitely practice that. And for the next one, going to be cotangent theta. Sorry for squeezing these in. Cotangent theta is going to be adjacent over opposite. That's 2 radical 7 over 6, which simplifies to radical 7 over 3. Okay, so there are our 6 trig functions of theta. Okay, so here is this next thing that we have here. We have the reciprocal identities. We have the quotient identities. So the reciprocal identities, that's something I mentioned on the first page. So it says sine is the reciprocal of cosecant. So that's what reciprocal means, right? It's essentially 1 divided by the value. So sine and cosecant are reciprocals, which this is why I wrote them right next to each other or right above each other. Cosine and secant are reciprocals, and tangent and cotangent are reciprocals. So you can definitely use that shortcut to help you do the ones, for example, that we just did. For the quotient identities means dividing, obviously. So tangent equals sine over cosine, and cotangent would just be the reciprocal of that, which is cosine over sine. So there's going to be tons of identities for these trig units. Okay, so let's say we are given sine of theta is 2/5 and cosine of theta is radical 21 over 5. We want to find the 4 remaining trig functions using identities. So let's do tangent first. So using the identities, obviously the identities above here, we can use that quotient identity. We know that sine of theta, or tangent of theta, equals sine theta over cos theta. So we can just plug in those values. It's 2/5 over radical 21 divided by 5. the divided by 5s ended up canceling. You could do this as keep, change, flip, keep the numerator to the same, change to multiplication, reciprocate the denominator. We would end up getting 2 over radical 21. Rationalize that denominator, we get 2 radical 21 over 21. So next one, let's do cotangent. So for cotangent, let's use the fact that that's 1 over tangent of theta. We could have also used the quotient identity and said it was cosine over sine. So what I'm going to do here is I'm going to use this version right here of tangent, because if we take the reciprocal of that, the reciprocal is just radical 21 over 2, and we don't have to worry about rationalizing any denominator. If we used this version of tangent and then we reciprocated it, we would have to rationalize a denominator. So just kind of thinking ahead a little bit. Next, let's do cosecant. So cosecant, reciprocal identity, it's the reciprocal of sine of theta. So you have to be a little bit careful because sine and cosecant are reciprocals. Don't get confused and say sine and secant are reciprocals. They both begin with an S, but that's obviously not why they're named that way, so just don't get confused with that. So the reciprocal of sine is 2 over 5, so the reciprocal is just 5 over 2. And obviously I'm not doing this the long way of saying 1 over 2/5, because that would equal 1 times 5/2, which is 5 over 2. I'm just skipping right to the reciprocal answer. Last one, we have secant. Secant is the reciprocal of cosine. The reciprocal of cosine, cosine was radical 21 over 5. So this would be 5 over radical 21, which is 5 radical 21 over 21. Okay, so make sure you know these identities. So some more identities now, they're called the Pythagorean identities. So the Pythagorean identities, there's 3 of them. We have sine squared theta plus cosine squared theta. If those thetas are the same, it's always going to actually equal 1. The next one is, so these are all the same exact identity. If we worked with this first one that we just did on the left, if we divide everything by sine squared theta, it would actually end up being this one right here. Sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared, thanks to the quotient identity. And 1 over sine squared is equal to cosecant squared. So these all are the same thing, just rearranged a little bit. And for the last one, 1 plus tan squared theta equals secant squared theta. That would be the original one with everything divided by cosine squared theta, and it would be rearranged a little bit. Okay, so these are the Pythagorean identities. So I'm going to do the quick derivation for why it's the Pythagorean identities. And I'm going to make a quick note here. So sine squared theta, or cosine squared theta, tangent squared theta, whatever. This is a shorthand way of writing it as sine theta and then squared. So the whole thing is being squared. The reason why we don't write it like the way on the right here is because then we don't need parentheses and it saves us a little space. If we wrote it as sine of theta squared, technically what this is doing is it's squaring the theta, so it would be something completely different. Okay, so let's see the derivation here. So Pythagorean theorem, we know that a squared plus b squared equals the hypotenuse c squared, right? So what we could do, we could divide, let's divide everything by c squared. So if we divide everything by c squared, we're going to get a squared over c squared plus b squared over c squared. C squared over c squared is equal to 1. we can actually rewrite this now as a over c squared plus b over c squared, thanks to our exponent rules. A over c, if we look at this angle right here, a divided by c, that's opposite over hypotenuse, so that ratio actually equals sine of theta squared. B over c, that's adjacent over hypotenuse, that would equal cosine theta squared equals 1. So that right there gives us our first Pythagorean identity. So that's just the quick little derivation for where this comes from and why it's called Pythagorean identity. Okay, so let's do this example. So given that sine of theta equals 3/5, and we're told that theta is between 0 and 90 degrees. So for right now, we'll see why this comes back into play in following sections. For now, kind of ignore it, but that does matter. So sine of theta is 3/5. Theta is between 0 and 90 degrees. We want to find cosine theta using the Pythagorean identity. So we want to use sine squared theta plus cosine squared theta equals 1. We know that sine theta equals 3/5. So this is going to be 3/5 squared plus cosine squared equals 1. So we need to solve this for cosine squared theta, and then square root both sides. So this is going to be 9 over 25 when we square the numerator and denominator. Now we have to subtract 9/25 on both sides. 1 minus 9 over 25. After we get a common denominator, we would end up getting 16 over 25. And then we would take the square root of both sides, and we would get cosine theta equals 4 over 5. The square root of 16 is 4. The square root of 5 is 25. Okay, so if sine of theta is 3/5, then cosine of theta is 4/5 when we're in quadrant 1. So drawing a triangle here, we can also see why this is the case. So let's say that this is theta. Sine theta is opposite over hypotenuse, so 3 over 5. We could do Pythagorean Theorem to find that missing side, and that would give us 4. So now we can see that cosine of theta is adjacent over hypotenuse, so 4 over 5. So when in doubt, try to draw a triangle. It won't always be that easy though. Okay, so for this last page here, we have trigonometric functions and their complements. So the definition of a complement is two angles are complements if their sum is 90 degrees. So for example, 70 degrees and 20 degrees are complements because they add to 90 degrees. 70 plus 20, 90 degrees, so we call them complements. Okay, so before we get into the cofunction identities here, let's also remember that the sum of the interior angles in a triangle is 180 degrees. So that means all three angles inside a triangle have to add up to 180 degrees. So if it's a right triangle, we automatically know that this one is 90 degrees, right? Because it's the right angle. So if one of them is called theta, then the other one right here, we can rewrite that in terms of theta. We know that this one and this one have to add up to 90 degrees. They have to add up to 90 degrees because the right angle is already 90 degrees of the 180 degrees. So there's 90 degrees remaining. So that means theta plus this other one has to equal 90. If we solve that for this missing angle over here, we can say that this equals 90 degrees minus theta. Okay, so with that, let's take a look at what it means to be for cofunctions. So taking a look at, let's look at sine of theta from this triangle. Sine of theta, theta's down here, so opposite over hypotenuse. Sine of theta equals a over c. Now let's take a look at cosine of this one. If we look at cosine of that other angle, once again, we have no idea what it is. We just know that it's 90 degrees minus theta. Cosine of that is adjacent over hypotenuse, which is a over c. These are both equal to a over c. That means they have to be equal. So that means sine of theta, whatever theta is, it's going to equal cosine of 90 degrees minus theta. Okay, so what that means is that sine and cosine are called cofunctions. So if you were wondering why sine and cosine sound so similar, it's because of that co in front is the only difference, and that stands for cofunction. It's just saying that cosine is a cofunction of sine, which is from the word complement. Okay, so here are the cofunction identities. So the other names, which I'm not going to get into right now, the other names like tangent, cotangent, secant, cosecant, they're all named those names for a reason. They're not just random names, but I won't get into it right now. So these cofunction identities, we have the one that I just said. Sine of theta equals cosine of 90 degrees minus theta. And it's actually the same in the other direction. Cosine of theta equals sine of 90 degrees minus theta. Tangent and cotangent are cofunctions. And secant and cosecant are cofunctions. So once again, hence the name tangent and cotangent, secant and cosecant. They're co-functions of each other. So what this means, if you think back to, we'll do the graphs and I'll bring this up again. This is going to be a horizontal shift and a reflection of each other. So sine and cosine, when we graph them, you'll see that all they are is a horizontal shift and a reflection of each other over the y-axis. But I'll mention that once we get there. So let's do these last couple examples here. So we have find a cofunction with the same value as the given expression. So sine of 72 degrees. So we're going to be using this first cofunction up here because it's dealing with sine. Sine of theta equals cosine of 90 degrees minus theta. So our theta here is 72 degrees. So I'm going to plug that in. Sine of 72 degrees equals cosine of 90 degrees minus 72 degrees. So all we have to do is simplify that. So sine of 72 degrees equals cosine of 18 degrees. So once we do a little bit more with these, we can show it on the calculator, but if you want to, you can plug that in the calculator now and verify that they're equal. And for the last one here, we have cosecant of pi over 3. So we're going to be using this last formula here on the right because it's dealing with cosecant. So cosecant theta equals secant. Instead of 90 degrees, we are in radians here, so we're going to be using pi over 2. So radians, we're using pi over 2 instead of 90 degrees, and that's minus theta. So cosecant of pi over 3 means theta is pi over 3, so we plug that in. And we simplify that right-hand side. Pi over 2 minus pi over 3, you would have to get common denominators, and it would simplify to pi over 6. So cosecant of pi over 3 is the same as secant of pi over 6. Okay, so that is the definition of cofunction, and that is it for this section.